Today's video will be on earthquakes. An earthquake is the shaking of Earth's crust caused by a release of energy. The energy that is released is in the form of seismic waves. In this picture, you can see that this target-looking picture is the release of that energy through those seismic waves when these two pieces of crust are moving by one another. Earthquakes can happen on fault boundaries, like you can see here, where we have a crack in a piece of crust, or they can actually happen at plate boundaries on our transform plate boundaries, divergent or convergent plate boundaries. So, like I was saying, where do earthquakes occur? They can be associated with large fractures or breaks in Earth's rocks called the faults. The San Andreas Fault is a fault line we've been talking quite a bit about. It separates the North American Plate and the Pacific Plate at a transform boundary. We've shown you how it extends through most of Western California. But also, we could have any kind of atomic explosion could definitely release energy and cause that rock to be moving around. Volcanic eruptions, sometimes we can tell when a volcano is going to erupt by small earthquakes that happen around the base because we know magma is moving around. And you can see here that they're also going to happen, all these dots in this picture, these are bordering the plate boundaries that we see on page 5 of our reference table. Okay, so they are coinciding with page 5 of our reference table because at any plate boundary we can have an earthquake occur. So what's going to cause an earthquake? Most earthquakes are caused by a strain or build up of energy along faults, which is typically near plate boundaries, but can be in between a lithospheric plate. They happen with no warning, so that's why they are so catastrophic when they do occur, because we don't know they're going to happen. We can figure out that, yeah, there is a lot of strain in that area and there's potential for an earthquake, but we cannot ever say the time and day. And they usually, the good part is they usually last only seconds, but the problem with earthquakes is that they create an offset of many buildings, so the aftermath of an earthquake is digging out of the rubble, maybe there's some fires, water lines, electric lines, gas lines, lots of things that are disrupted during an earthquake, which causes a lot of major problems. Over 1 million earthquakes happen per year, but you don't hear about those million every single year because most are small, and we call most of them instrumental, meaning people don't really notice that they're happening. About 75 per year are significant earthquakes that you're going to hear about on the news. And the reason you're going to hear about them on the news is because they're going to cause destruction to buildings, deaths in an area, and that is normally what news would cover. Okay. Sometimes, even if it is a significant earthquake, they're going to happen in remote regions, so there's really no deaths associated with it, no catastrophes, so they don't really make headlines in the news. But when they do hit those largely populated areas, they are said to be most of the destructive forces on Earth. And like I was saying before, fires can break out because of broken gas and power lines. And then people tend to be trapped in buildings for a long amount of time because these long, tall, skyscraper type buildings can just fall and crumble due to that earthquake. The only warning that you can possibly get that a larger earthquake is going to happen would be a foreshock. This is a small earthquake that happens before a major earthquake, and then after a major earthquake you can also have an aftershock, and these are small earthquakes that happen after a major earthquake. But sometimes when you have, like a 7.0 on the Richter scale, you can get an aftershock that's in maybe the 4s or the 5s, which really is going to be quite a bit of shaking and could potentially cause damage. So your foreshocks and aftershocks are really the only thing that we use to predict these earthquakes. Throughout the rest of this unit, we're going to be talking about the focus and more specifically the epicenter. Okay, the focus is the underground point of origin of an earthquake. This is where the actual rocks are breaking and moving. The epicenter is directly above the focus on the Earth's surface, okay? And that's where the earthquake waves reach first, and the most violent shaking is found here. So we always talk about finding the epicenter of an earthquake because that's where that energy started and where we're going to see the most destruction on Earth's surface. So if you take a look at this picture here, the focus is underneath the ground where those rocks are breaking. You can see the fault line here. That's exactly where the fault lines, the focus is, where the rocks are breaking apart and the seismic waves are moving out from there. And the epicenter is directly above that on the Earth's surface. Okay, so seismic waves, I've been saying that a lot throughout this video. These are those earthquake waves, okay? Seismologists are going to study them. So a seismologist is someone who studies earthquake waves or earthquakes. Okay. There are three types of waves we're going to talk about: primary or P waves, secondary or S waves, or surface waves, which are L waves. The primary waves are body waves. They travel through Earth's interior. They're called push-pull waves. They're compression waves. Okay, so they kind of do a tug-of-war back and forth motion. And the really important thing here is they travel through solids, liquids, and gases. They can travel through anything. They are the fastest seismic wave. That's why they're called the primary waves, because they arrive first. S waves are secondary waves. They travel through Earth's interior as well. These are side-to-side waves. They kind of have that amplitude to them. They rise and they fall. And they only travel through solids. So I always remember the secondary waves. They start with an S. They can only travel through solids. They don't move as fast as P waves. They come second. That's why they're called secondary waves. So if we look at this picture here, the top one here, this is the push-pull, okay? So it's moving back and forth. And then this is the shear or the side-to-side wave, which is your S. So if we watch a quick animation, if you watch that blue ball there, you can see that's the push-pull motion of the P wave. And I'll play it one more time. You can see the push-pull compression waves of our P waves. And then look at this one over here, watch the blue ball again. These are S waves, the side-to-side waves. So these are more like a normal wave that you would think of. They come second, and these are our side-to-side waves, or our S waves. Remember, S waves only travel through solids. The final wave is called a surface wave or an L wave. Okay, these are longer waves. They're the slowest moving, and sometimes you don't even get these when you have an earthquake, but they originate on the Earth's surface at the epicenter. They move like waves on an ocean, okay, and they're gonna move up and down. They only travel on the surface. That's why they're called surface waves. But if there are surface waves involved in an earthquake, you know it's going to be a serious earthquake because they do cause the most damage. They're going to bend and twist the Earth's surface and really cause a lot of damage on that surface. So as a quick check here, think about the three types of seismic waves that seismologists study and what materials they travel through. So your P waves are going to travel just through solids, liquids, and gases. Your S waves just through solids, and your L waves are your surface waves. A seismologist is going to read seismic waves on a seismograph. Okay, a seismograph is going to be the instrument that detects and measures the seismic wave. It has like a piece of paper and a needle, and it records the vibration on the surface. A seismograph will produce what's called a seismogram, and a seismologist is going to look at the seismogram. So this would be a seismogram here showing you the P waves and your S waves being recorded. Okay, the higher the line, so you can see higher lines here, that means the stronger the earthquake is going to be. So what we're going to need here to figure out where the epicenter of an earthquake is three different seismograms to find the exact location. This is called triangulation. Okay, now triangulation happens meaning we need three separate locations because if I didn't have three, I wouldn't get one single location. Okay, so if you look here, this right here is seismogram 1, this right here is seismogram 2, and this right here is seismogram 3. Okay, they will all intersect at location B. So you can see the edge of all three of these circles intersecting at location B, telling us that it is, this is the epicenter. If I only had these two circles, okay, on the outside, and I didn't have this one out here, then I would either get two places for this to happen, either at B or over here. That's where they intersect. So you need 3 to figure out where the epicenter is going to be. Now, sometimes a seismograph will only receive P waves, and they will not, or they might not receive any at all, okay? This is because, remember, P waves can travel through everything. S waves can only travel through solids, okay? So if a seismograph is only receiving P waves, that means those waves had to travel through the outer core. If you remember, the outer core is liquid. So if you do not receive S waves, that means that those waves had to travel through the outer core and were absorbed by that liquid, okay? If no waves are received, it's because the seismograph is in what's called a shadow zone, okay? So what does that mean? If we look at this picture, okay, here you can see P waves are only received because these waves traveled through the outer core, so the S waves were absorbed. They cannot travel through liquid. A, B, C, and D, P and S waves are received because they're traveling through that solid layer, and everything can travel through solid, so they all made it there. But then you'll notice location E here is called a shadow zone. No waves are getting there because as the waves hit the liquid outer core, they refract or they bend, okay, and change their direction. So these waves here, if they didn't hit the outer core, they should have made it all the way to E. But because they change from a solid to a liquid, refraction occurs and we end up with this shadow zone. Okay? So this bending of earthquake waves, or the refraction of the waves, is why we get our shadow zone. Okay? So a shadow zone is just an area that does not receive any seismic waves.